let's talk about a boat problem. Now, when we do these word problems, we've got three main types of problems that we have going on. No, don't do that to me. One type of excuse me. I'm the one making this video, not you. Although you can subscribe, thank you. Now, there are three main types of word problems we're going to come across. One was what we just saw, where you have words and you write the equation straight from that. That's all it is. Then you've got problems like this, where you have a boat or a plane that's being affected by the current in the river, or maybe by the air when you're flying, because if you're flying into the wind, it's going to slow you down. If the wind is blowing at the back, call it a tailwind, it's going to speed you up, right? That's another type of problem. And then what we're going to see in the next video will be what we call a work problem, where you have two people that can accomplish a job at different rates. What happens when they work together? But this is a problem that we shouldn't mess up on. And I'm going to write something here that you should all write down. It should be almost like a formula that you write. We're talking about a boat that, if it's in still water relative to the shore, it's traveling at 15 miles per hour. Okay? And it can travel 36 miles downstream, and at the same time it can travel 24 miles upstream. These are real words that we're using here, and you need to understand what upstream and downstream are. And of course, if you guys go out into the middle of nowhere, you can find those rivers, and you go cruising down them, trailing your cooler full of
beer, baby.
Not beer, of Capri Suns, okay? But you know about going upstream and downstream, right?
Yeah.
You know that if you happen to miss a spot, you've got to paddle against the current going upstream, right? Okay. Now, when you want to talk about your overall rate, your overall speed, your overall rate is going to be the speed of the boat, or speed of the vehicle, whatever it happens to be. It's the speed of the vehicle, I'm going to say, with no current or no wind. It really depends on the situation. And then plus or minus the speed of the water or wind or whatever it happens to be. So your overall rate, like if you just take how fast does the plane normally go? How fast does the boat normally go? Okay. But then you're either going to add or subtract it based on what direction you're going in with respect to the external forces, right? Does that make sense? So like if you're going with the current, you get to go what? Faster. But if you're going against the current, you're fighting against that and you go slower. Okay? So this is super important for you guys to know, because when we're talking about these distance, rate, and time problems, this guy comes into play. So speaking of distance, rate, and time, that's what we're working with here.
Is that a box thing you're supposed to do?
That's what I'm going to do. Remember that your distance is equal to your rate times your time. Now, you've got two situations that are being described here in this word problem. Okay? In one of those situations, you are going upstream, in the other, you're going downstream. So I need you to tell me what we know about going upstream and downstream. Easiest thing to start with is probably your distance, because it gave that to you. What do you know about your distance?
Oh, okay. Downstream is 36 miles.
So you travel 36 miles, it says you travel 36 miles downstream, and the same time it takes you to do what?
Go upstream 24 miles.
Travel upstream 24 miles. Do you know anything about the time or the rate?
Lap per hour, 15
Miles per hour is a rate, isn't it? But here's what you need to do. This 15 miles per hour is the speed of the boat with no external forces acting on it, right? So when I come down here, I need to figure out how I'm going to write this up. Look, your overall rate, I told you, here's this formula. The speed of the vehicle, then plus or minus the speed of the water. So what's the speed of the vehicle normally with no current? 15. So I'm going to put that here for both of these. But then here comes the next part. You have to figure out what gets to be added and what gets to be subtracted. When you go upstream, are you adding or taking away from your speed? Upstream, you're losing speed, right? Then when you go downstream, you get to add. So in this case, you get to add or subtract the speed of the current. Do you all agree? So what's the speed of the current?
Well, you have to find the speed of the current.
Oh, we don't know it, do we?
Yeah.
So what we have here
Minus x or plus x.
is that x is going to equal the speed of the current. X is equal to the speed of the current. So when you're going upstream, you're going to take away the speed of the current. When you go downstream, you get to add the speed of the current. Do you all agree with that? Now, what about your time? What does it say about the
You
time?
have to go across, so it's 24 times 15 minus x equals time.
No.
No.
Distance equals rate times time, not time is distance times rate.
So it equals to 24 then. So it'd be x times 15 minus x equals 24. What you just said is equal to.
No. I said the distance is the rate times the time, but you don't know the time.
It's going to be x.
Your time cannot be x because x is the speed of the current, isn't it?
So it has to be y.
If you want to introduce another variable, you can, although I don't recommend you doing that. Here's what we know, though. You know that your distance is equal to your rate times your time, right? Okay. So how do you represent your time?
Minutes, hours.
Based on distance and rate, how do you figure out your time?
Oh, divide. You have to divide it.
Don't you divide by the rate? Your time is your distance divided by your rate, isn't it?
Yes, it is.
Your time is your distance, 24, divided by your rate, which is 15 minus x. What's the time going downstream?
Oh, 36.
Your distance, 36, divided by what? 15 plus x. That's how we can represent the time. But notice, what does it say about the time in the problem?
Find the speed of the current.
What does it say about the time here, number 3? 15 miles per hour is a rate, not a time.
So you're trying to figure how long it's going to take?
The same amount of
Well, it
time.
says find the speed.
It says the same amount of time, doesn't it?
Mhm.
So whatever your time is going upstream is the same as the time going downstream. So what does that mean to you as an equation?
An equal?
It means they're equal, right? So it means when I look at this, that means that 24
Divided by 15
over 15 minus x is equal to 36 over 15 plus x. Bless you.
That's crazy.
So think about what I told you here in this problem. I said that it was going to be the same amount of time, but we had to find expressions for that time. And I was able to find that because I knew my distance and I had a way to represent my rate. And since distance, rate, and time are all connected, time is just the quotient of your distance and your rate. We said these guys were the same, so now we have this equation to solve. How are we going to solve this guy?
So 24 times 15 plus x equals 36 times 15 minus x.
24 times 15 plus x equals 36 times 15 minus x. Okay? Now, you can make your life a little bit easier if you want to. You could go ahead and distribute this out, and I've got no problem with you doing that. But you know there's a common factor on both sides of the equation. What's the common factor? You can do better than that. 12 is a common factor, right? So if I divide both sides by 12, this guy becomes a 2, this guy becomes a 3. So your numbers are a lot easier to work with. You don't have to do that, though. I do that because I like to have smaller numbers when I'm working with math. All right, so we have what? Distribute with a smaller number now. What do you have?
45.
I've got 30 plus
2x.
2x equals what?
Equals
45 minus 3x?
minus
Is this quadratic or linear?
linear.
It's linear, so what am I going to do?
We should put positive x
Move the 3x to the left side, so I have what?
plus 3x over here minus 30 over there.
5x equals 15.
All right, 5x on one side, subtract the 30, and I get 15.
And x equals 3.
X equals 3. Now, what did x represent?
Speed of the current.
Speed of sound of
X was the speed of the current in the river, so the question says find the speed of the current in the river, so we can say what?
3 miles per hour.
Right. So we can say that the speed of the current is 3 miles per hour. Does that sound appropriate? Well, I want you to think about this. Come back up here to your chart. If you're going upstream, that means you have an effective rate of what?
15 minus 3.
So you are effectively going at 12 miles per hour, right? What about when you're going downstream, when you get to add the speed to your
18 miles.
other country's speed? So we get 18 miles per hour. How long would it take you to travel 36 miles at 18 miles per hour?
18.
It'd be 2 hours, right? How long would it take you to travel 24 miles at 12 miles per hour? 2 hours, so you see the time would be, excuse me, would be the same, right? All right.
You kind of use that still, but it's not, you don't think about it that way.
The big thing to know here that you're going to use later is going to be this guy that's here in red. When you have these problems where you've got wind or water that's speeding you up or slowing you down, you need to be able to write the rate in terms of its two components, the speed of the vehicle without any resistance or help, and then see the plus or minus the speed of the water or the wind. That's the important part. It's always the vehicle first. Always, always, always. If you didn't know the vehicle speed, you would have put x first and then plus or minus the speed of the current. Are you with me on that? So to pay very, very close attention to that.